like to thank the committee members for giving me the opportunity to defend my thesis here. So I'm going to talk about lyotropic chromonic liquid crystals. So first I'm going to talk about experimental study of the viscoelastic properties of them. Then a non-equilibrium active system composed with chromonic liquid crystals called living liquid crystals. So chromonic liquid crystals is not like 5CB or MDBA that you can only find in the fridge in your lab. It's a material that is abundant in our daily life. 90% of the food dyes that you encounter every day can form chromonic liquid crystal phase. So two materials I'm going to talk about today, sunset yellow is a food dye, and disodium chromoglycate, or DSCG, is an anti-asthma drug. So these molecules have a plank shape with aromatic cores in the center and ionic groups at the periphery. So without these flexible acyl chains, they are safe to biological systems ranging from bacteria to humans. So when you dissolve this kind of molecules in water, the ions at the periphery of the molecules get dissociated. And this plank shape, because they have a aromatic center, they don't like water. These molecules stack up into cylindrical shaped aggregates. And these aggregates are typically along about tens of nanometers long, and the diameter is 1 to 2 nanometers. The stacking distance between the molecules is about 0.34 nanometer. And this scission energy, defined as how much energy you need to pay to break one aggregate into two, is on the order of 10 kBt. The scission energy comes from two parts. One is attraction between the aromatic center, the van der Waals force. The second part is from the repulsion of the surface charge of these aggregates. Because the positive ions, like the sodium showing on the left picture, get dissociated, the surface of these aggregates are actually negatively charged. When you have enough of these aggregates in the solution, they start to form pneumatic phase, similar as what Onsager described. As you can see here, the lengths of these aggregates are not fixed, but rather they are a function of concentration and temperature. Also, one can notice that the temperature dependence is on the exponential part. So this gives us an interesting question to ask is, since the mechanism of lyotropic chromonic liquid crystal to form is so different from the thermotropics, like 5CB that everyone uses in the lab, how the viscoelastic properties of such material can be different from a normal thermotropic liquid crystal. So we do the experimental study to measure the viscoelastic properties directly. So two kinds of experimental techniques were used in our study. The first one is a classic Friedrichs transition. So when you put the uniform cell of chromonics, either planar or homotropic anchoring into a magnetic field, and you apply Shuang field, the field will distort the director field. And from the optical appearance, you can determine the K1, K2, and K3 values. But you have to measure the delta chi in a suite device separately. A second technique is called the dynamic light scattering. There, from the thermoflagellation of the director field, you can measure the depolarized light as a function of angle and time. So from this information, you can not only deduce K1, K2, and K3 values from the experiment, you can also get the three viscosities associated with this deformation: eta splay, eta twist, and eta bend. So I would like to present part of the result here. So in the dynamic light scattering experiment of DSCG, we see several interesting things. First of all, the K1 and K3 values are comparable to each other. They are on the order of tens of piconewton. This is comparable also to thermotropic liquid crystals such as 5Cb, but the K1 value of such material is extremely small. It's on the order of 1 piconewton. Also, you notice that K1 value of DSCG grow exponentially with temperature. The Frank-Elastic constant can also be tuned by changing the ionic components in the system. So in a separate experiment done with sunset yellow, we fix the concentration of sunset yellow in the water solution, but at different amount of sodium chloride. So in this case, you can see that the K3 value decreases as you increase the concentration of sodium chloride. But if you replace the sodium chloride with magnesium sulfate, you see a different trend on the different parameters. So K1 value, the splay constant, increases as you increase the concentration of magnesium sulfate. So the dynamic light scattering gives us direct access to the viscosity. So here the result is even more astonishing. So the splay and the twist viscosity are on the order of 1 to several hundred Pascal second, which is 2 to 4 orders of magnitude larger than the band viscosity, and the band viscosity is comparable to the band viscosity of 5Cb and other normal thermotropic liquid crystals. And also you can see a clear exponential dependence on temperature of the splay and the twist viscosity here. So how we explain our findings? We use a model designed for lyotropic liquid crystal with flexible aggregates. So in such model, the splay constant is associated with the contour length of these aggregates. So splay deformation tends to induce density difference. It's like splitting your fingers, you immediately create vacancies in between your fingers. So to conserve the density, you need to find a free end of other aggregates to fit into these vacancies. So the longer the aggregates, the harder it is to find a free end to fit in. That's why the K1 value is associated with the length of these aggregates. So the length of the aggregates is has this exponential dependence of the scission energy E and temperature T. So that's why in the first result I show, when you change the temperature, the K1 value changes exponentially. Also, when you add salt into the system, you screen the repulsion between the surface charges, and this effectively increase the scission energy E here, and also cause the increase of the K1 value. But the K3 value associated with the band deformation is a different story. The band deformation is not restricted by the length of the aggregates as long as these aggregates are flexible. So a determining parameter here instead of the length is the persistent length. So when you add salt, for example, sodium chloride, into the system to screen the surface repulsion, it's become easier for the aggregates to bend. So the flexibility of the aggregates increase, then as a result, the K3 values decreases. As I shown here, the change of the K3 values depends quadratically on the Debye screening length, which is associated with the concentration of the sodium chloride in the system. The viscosity of such system is exponentially large compared to 5Cb. That's because in 5Cb, the basic building units are molecules. They are very small. But here, the basic building units are long aggregates ranging from 20 to 200 nanometers. So when you have long aggregates and when you induce twist or splay deformation, you actually induce considerable flow field in the system. And the energy dissipated by rotating a rod of length L in the flow field is actually proportional to the length square. So if you look at the PowerPoint slide carefully, the exponential component for K1 is 0.2, but for eta splay and twist is 0.4. That confirms this theory that eta for splay and twist is proportional to the length square. But for the band viscosity is different. So band deformation doesn't involve this flow field as described here, but rather these aggregates are just sliding against each other. That's why this viscosity is low. So far we have talked about studies in the equilibrium state of material. There exist a variety of systems in our life that are intrinsically out of equilibrium. They are called active systems. So in active system, like bacteria, swarm, or fish schools, each individual is powered by the internal source of energy to drive the motion. And this driving and interactions through the flow field and other interactions often leads to the orientational order in such system. But now, since we have the biocompatible chromonic liquid crystal, we can compose this new active system called living liquid crystals. So here, we don't rely on each individual swimmers in the system to give us an order. We superimpose the order with the chromonic liquid crystals. In such a way, we achieve independent control of the activity, how much activity we have in the system by tuning the concentration of the bacteria, and also can be done by tuning the oxygen concentration in the system. And also we can control the orientational order of the system simply by playing with the concentration and temperature of the DSCG. So the interaction between the activity and the superimposed nematic order give us a lot of interesting phenomena. So first of all, these bacteria, when they are at very low concentration and very far away, separated from each other, they are influenced only by the nematic liquid crystal. So shown here is that when bacteria swims, they actually follow the director of the director. So here you have an isotropic melt which creates this curved boundary, and in the nematic background, the director field is aligned parallel to the boundary. So when the bacterium approach, it swims along this boundary. So from, if you look closely at one bacteria, you see these interesting patterns, these alternating black and white dots that are traveling backwards. So you can get useful information from this pattern by just looking at them at different time frames. So from here you can deduce useful information like the pitch of the flagella rotation is 2 micron, and the frequency of the head rotation is 2.5 Hz, while the tail rotation frequency is 16 Hz, and the swimming speed is about 15 micron per second. So these flagella are only 24 nanometers thick. It's hard to see in other ways, but the birefringence of the chromonic liquid crystal give us opportunity to directly observe their motion with a simple polarizing microscope. We can also change the state of the system from equilibrium to non-equilibrium simply by the oxygen availability in the system. So here we have a high concentration of the bacteria, and when we don't have oxygen supply, the bacteria aligns parallel to the director field. And since the director field is pre-designed to be uniformly planar, you don't see much texture here. And the activity, when activity is 0, you have a uniform director field corresponds to the equilibrium state of the system. But when you turn on the activity by supplying the oxygen, these bacteria start to move, and as a collective result, they distort the director field around them. They create this periodic band deformation, which is showing on the polarizing microscope here, and schematic like this. So when activity is bigger than 0, the director field becomes periodically distorted. So here is a movie of the actual experiment. So we didn't control the oxygen supply here, but this system just take some time to evolve into this steady state of the non-equilibrium steady state. So in the last, you can see this periodic patterns shown here. So what determines the size of the periodic pattern? We built this simple mode by balancing the torque generated by the bacterial flow, this term here, and the torque generated by the distorted liquid crystal. And the balance of these two give us a coherent length psi, which is in proportion to the square root of k over activity, basically. So we can tune this amount of activity by bacterial concentration. So we conducted an experiment shown just before at different conditions. Then we found that they more or less follow our simple model. We can further increase the richness of the system by putting more bacteria here. Then this oxygen gradient in the sample give us a constant tuning of the activity in such system, that you can see the system from a uniform state, not shown here, to a fully developed active state. There are two transitions in the middle. So the first transition is when you just turn on the activity, you start to have this periodic band deformation. But when the activity is increased to even higher value, this band deformation becomes unstable again. And as a result, you have the creation of the topological defects of plus half and minus half. These defects are being constantly created and annihilated, and they are constantly being rearranging themselves in the system spontaneously. So these two scenarios, two transitions, has been predicted by several theoretical groups, but we have shown very conveniently in one experimental system that you can really achieve this. So as a summary, in the first part, I talk about the viscoelastic properties of the chromonic lyotropic liquid crystal. And the K1, the splay constant there, is proportional to the length of the aggregates, while the K3, the band constant, is associated with the persistent length of these aggregates. We can add ions to tune these parameters in different ways. The viscosity, the splay and twist viscosity in such system is proportional to the length square of these aggregates, and that's why they are so exponentially large and change so dramatically with temperature. The second part, I talk about the living liquid crystals, where the single bacterial motion can be controlled by the pre-designed trajectory of the director field, and the birefringence of the director field enables us to visualize some tiny features that is hard to visualize otherwise. And the competition between the activity of the bacterium and the nematic order of the system give us a way to describe the system through this coherent length psi here. So I would like to thank for your attention, thank the committee members, thank my advisor, Lyotropic, for seeing me through these years, and thank everyone else. Thank you.